All right, so we are going to go through a question on maximum power transfer. So this question was a request by someone that we go through it, and I'm not really talking about maximum power transfer or AC power comprehensively. I'm just answering this question that have to do with maximum power transfer. And as I answer this question, I'll try my level best to talk about as many concepts that are attached to maximum power transfer as much as I can. Yeah, so before I continue, just in case you're new to the channel, consider subscribing, ring the notification bell so that each time we upload new content, you be notified. We have a lot of content that is coming up, which is very very exciting, and you would not want to miss out. Okay, so when it comes to this question, there are there are two main things that we are concerned with that we really have to find. So in this case, first of all, the question is saying for the circuit below, find the load impedance that absorbs the maximum power average. Um, that absorbs the maximum average power. Then after that, we need to calculate that maximum average power. So the thing is that we are looking for the load impedance, the one that's indicated as ZL. All right, that's the one that we are looking for. So in this case, the concept is about maximizing power. What do we do when you're maximizing power? What do we understand? So the first key thing that you have to understand is that when you maximize power in a circuit, what you're doing is that you have reduced energy loss in that particular circuit. Okay, so the first thing that I would want to highlight is that if you're going to have your load resistance, okay, I believe we get this concept from Thevenin and Norton part. If you have your load resistance being equals to um, your Thevenin resistance there, okay, if these two are equals to each other, then uh, maximum power is going to be delivered to the circuit. You're going to have maximum power being delivered to the circuit that you have, provided these two are what are equals to each other. All right. So now, we are going to use a similar concept here. Okay. So, and another thing that I would want to put across is that when you're maximizing power, it's just a thing of you matching the circuit and load impedance. It's like you have your circuit impedance, which is the the Thevenin impedance indicated as that, and you have your what? You have your load impedance. Okay, you have your load impedance. So matching these two is really going to give us that maximum power that we have. Okay, so once again, as a result, if you have maximum power, we are going to minimize energy loss in that particular circuit. So keep in mind, overall power is just equals to it's just more like the product of voltage by current. But of course, this we talk about this more of this on DC. But when you talk about AC, of course, you know you have to deal with phases where you have your cos, the phase angle of the voltage minus the phase angle of the current, of course, divide by 2 there. And this can also be expressed as what? If you're talking about power, absorbed power that is absorbed by a load, where you're going to say 1 over 2. So you know to say voltage is simply equals to voltage is equals to current by what? By resistance. So you come here, you say your current multiplied by resistance by this current here. Okay, that current there. So this is going to give you what? 1 over 2 multiplied by uh, I squared, or current squared by what? By the load resistance that you're talking about. Okay, so now this gives us this simply gives us uh, the maximum power that is delivered to a load, where you say your power is equals to 1 over 2 I squared times R, like that. That gives you the maximum power delivered to the load. Let me put L there, like that. Okay, so having said that, how then do we come up with what? The load impedance, where we are going to have a maximum power. Okay, so the thing is that this part we have to keep it in mind as well. Okay, we have to keep we have to keep that part in mind. So all we have to one of the things that we have to remember is that I'm going to highlight how this comes about a little bit later, is that your load impedance, okay, your load impedance that you are looking for maximum average power transfer is equals to the what? the conjugate of the what, of the Thevenin impedance. So if you have found your Thevenin impedance, okay, if you have found your Thevenin impedance, the conjugate of that, the conjugate of what you have as your Thevenin impedance is going to give you the what, the load impedance, and you have simply found the solution that you are looking for. So it's just a matter of you finding your Thevenin impedance, which is the way you find the Thevenin impedance for in this case, the same way you find your what, your R Thevenin. Okay, the same way you find your R Thevenin, use the same concept to find what, your Thevenin impedance. Yeah, then the conjugate of that, the complex conjugate of what you get, that's going to give you the what, the load impedance. Right. Then what about I think from what I've talked about, we are able to come up with what? We are able to come up with the Thevenin impedance, which is going to give us the load impedance. We cannot talk about how do we then calculate that the maximum average power that we are looking for. So the formula that we are going to be using for P max, or maximum average power transfer, is going to be equals to is going to be equals to, you're going to have the absolute value of the Thevenin voltage squared divided by 8 multiplied by what? By the R Thevenin. So how does this equation come about? There isn't much to do when it comes to how that equation comes about. It's the fact that initially you're going to say your Thevenin your Thevenin impedance will be equals to what? Is equals to your 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 R Thevenin plus what? Um, the part that I'm going to indicate as JX Thevenin. Okay, then you're going to have your load impedance, which is going to be equals to your load here. Okay, your load resistance plus your JX load there. So now, uh, when it comes to Thevenin theorem, we were talking about current being equals to the Thevenin voltage. Okay, Thevenin voltage divided by what, by R Thevenin plus what, plus the load resistance. Similarly, that's what I'm going to do here. I'm going to say at this point, um, this is going to be Thevenin impedance plus what, plus load impedance there. Okay, so meaning when it comes to this part, you can say we can hence say the current is going to be equal to the Thevenin voltage divided by what is our Thevenin impedance, is equals to what, R Thevenin. Okay, R Thevenin plus uh, our JX there, Thevenin. By the way, this part this part here, okay, this part that you have here and this part, they are just simply talking about it's just simply talking about the reactance of that circuit that you have. Okay, it's just simply talking about the reactance of that circuit that you have. So remember, initially I had said for us to come up with a maximum average power transfer, it's just a matter of us matching the circuit and the load impedance, which is what you have here. Your v your Thevenin impedance is your circuit impedance. Okay, then you have your load impedance as your load impedance, of course. So matching those two is what is going to give us the what, the Thevenin that's what going to give us the maximum what, maximum average power transfer. And how do we get that maximum average power transfer? We get it from the current. Okay, if you have maximum current, you're going to have maximum um, average power transfer. So remember to say at this part you're also adding the what, your load resistor plus what, uh, plus the reactance of the circuit there. Okay, so let me erase this part. Okay, we'll bring this back if we need it. Let me just erase it for now. So we have said the current is now equals to your V Thevenin divided by what? Divide by, I can pair these two together. I can say, okay, I have my what? Thevenin resistance plus load resistor plus here I can factor out the J, which is the for complex. Okay, that's going to be the circuit reactance Thevenin here plus what, um, the circuit reactance where you have a load there like that. So now, um, this part here that you have, okay, so the thing now is that the bigger the value of the denominator, the smaller the value of the current. But remember, for us to get the maximum average power transfer, the current needs to be maximum. So what I need to do is that I need to maximize this, what I need to maximize the current that I get. So the bigger the denominator, the smaller the current that I have, because these two are inversely proportional. So now the thing is that for us to get the maximum current from this is that the denominator needs to be as smaller as possible. Okay, so now you observe to say I cannot change this because those come with a circuit. It's like you've been given a resistor value of 5, like you don't need to make any adjustment to that. But for the part of the reactance, we are able to do something. Okay, so I need to minimize this part as much as I can. All right, you need to minimize that part as much as you can. So the best way to minimize that is having this almost equals to that, but opposite in terms of what, in terms of polarity. If this is positive, let this be negative. It's such as maybe I have positive 9 here, then here let me have something like maybe let me say 8.999, let me say negative. Okay, so now the thing is that here I'm going to get a very very small value, but I don't think I want to go that route. For convenience's sake, let's just set our uh, x7 in there to be equals to what, x load there. So if these two are equals to each other, meaning they're heading towards 0, and we can simplify this by saying, okay, I will be equals to what, v7 in divided by what, r7 in plus what, uh, the load the load resistance there. Okay, so now this is going to give us the what, this is going to give us the maximum power. We have done something with this part, because remember to say we are going to add anything that we have here, and once again, the bigger the denominator, the smaller the value of the current that you have, because of the proportionality kind of relationship that they have there. All right, so now how do we then come up with that formula that we have that has like it's where we say P max is equals to we said P max, let me just write it somewhere on top here. P max, we said P max was equals to absolute value of V Thevenin squared divided by what, 8 multiplied by what, R Thevenin there. Okay, so now keep in mind to say we said the 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 power, okay, the maximum power that is delivered to a load is equals to, where you have your P is equals to 1 over 2 I squared by load resistance there. Okay, so you're going to come here and say, okay, you're going to say your power is going to be equals to, of course, let me just say P max there for convenience's sake. P max is equals to, I'll have 1 over 2, where there's I here, okay, where there's I, I'm going to put V7 divide by what, divide by R7 plus R, the load resistance there, then squared multiplied by what, the the load resistance there again. So what we are going to do here is that we had said initially, for us to have, this is where it gets interesting. We had said for us to get maximum power, for maximum power to be delivered to a circuit, your RL needs to be equals to your R Thevenin. So in this case here I can substitute, where I have RL, I'm going to put R Thevenin. So this is going to be something like 1 over 2, I'll have like V7, okay, V7 divided by, here you're going to have, I'm going to substitute with R7 in there, which will just give me something like 2R 2R7 in there squared by load resistance there. Okay, so let's try to break this down. This will be 1 over 2, that will give us something like V7 in squared divide by that's going to give us 4, then R Thevenin squared by what? This part again, we can still equate it to what? We can still make that to be R Thevenin because of what we have to have talked about here. So overall, the whole idea is just about what is the whole idea is just about us maximizing the power that we are supposed to get. Okay, so let's continue breaking this down. So we're going to say our power is going to be equals to, that would be your V Thevenin squared divided by 2 times 4, that's going to be 8. Then you still have your R Thevenin multiplied by R Thevenin, giving us R Thevenin squared. This and that are the same thing. I'm just writing like this for convenience's sake, so that you observe to say this can go and that can go. So P is going to be equals to, here I can just put an absolute value for some reason, and I'm not going to tell you that reason for now, and we are going to observe that reason as we perform the calculations. So P is going to be equals to absolute value of the V Thevenin squared divided by what? Divided by 8 R7 in there, and that's the maximum average power transfer formula that you're going to be using. Okay, once again, I'm still wondering why I keep on forgetting to write Pmax. Okay, so this is Pmax there. That's not just any power but maximum average power transfer. I need to show that difference. So divide by 8 R7 in there. Okay, so this right here is the formula that we're going to be using to come up with what? To come up with the maximum average power transfer. Okay, so remember, first of all, determine what your Thevenin impedance is. Then the complex conjugate of that value that you have is your load impedance that we are looking for. And like, how do we come up with that one? It's just simply, we said it's the same way that you used to find the R Thevenin. If you have some independent sources in the circuit, switch them off, just like we have right here. I have the current, so for me to come up with the Thevenin impedance, I have to switch that off. So now the thing is that you always have to remember that when it comes to a voltage source, there's when you have a voltage source and there's when you have a current source. So if I switch off my voltage source, what am I going to have? Is it a short circuit? Is it an open circuit? Keep in mind, if you switch off a voltage source, what you're going to have is a short circuit. It's just more like a line, just a wire. Okay, and for this one we say resistance is equals to what? Is equals to 0. If you switch off a current source, okay, if you switch off a current source, what you're going to have is what? Is an open circuit, of which resistance is going to be equals to what? Is going to be equals to infinity. It's just way too big, so there's no need of putting anything here. Like, it's just going to be nothing. Like, this part is going to be eliminated. Okay, that's when you switch off a current source, and that part is very, very, very important. We always have to remember to say voltage source, short circuit, opens current source, open circuit. And the thing is that there, for a short circuit, you have resistance being equals to 0, you have 0 resistance. Of course, a material on its own, it has its own resistance. That has to do with what? The either the material that was used to make that component that you have, or I could say more like the shape. It has to do with like the surface area, the cross sectional area, as well as the length. Okay, so what I would do is that I'm going to end here on this video. Make sure to say you watch the next video. That's where I'm going to go through the calculations. I thought I was going to do the calculations just in this video, but it appears that would be way too long. So the calculations, they are going to be in the next video. I'm glad I talked about almost everything just within this video, and I believe that's clear. And I would advise you to go through the question, try to solve, then watch the video that is coming next, so that you try to make the comparison and see whether we are going to have the same solutions or if they are going to be different. If they are different, why are they different? Of which, feel free to get in touch through the comment section down below. Otherwise, thank you very much for watching.